Hi everyone, welcome to Chemistry 12.2. This is the second and final video for Thermochemistry, Unit 1. I wanted to take a minute to talk a little bit about multi-step calculations and to do one example with you. If you take a look at the PDF that's posted for section 17.4, there are a few other multi-step questions included there, and the answers have been done out for you, so if you want to take a look at those. Multi-step energy calculations are really just problems that may involve more than one concept that we've talked about in thermochemistry. Practice energy calculations rarely involve just one single calculation of heat or enthalpy. In most practical situations, several energy calculations might be required. So what we've been building, and it seems like it's been a long time because of our time away, but what we've been building in this first unit is kind of a toolbox, and we've been putting some different techniques into that toolbox. And now we've got all of these techniques, and we're going to see which ones work best to solve these problems. For example, we started off talking about heat flow, Q versus enthalpy change. We looked at the tiers of energy changes, and that first tier was when we had temperature change, when kinetic energy was involved, not potential energy. So Q equals mc delta T, or Q equals big C delta T, that was bomb calorimetry. Then we looked at tier 2, and that was when we had phase changes, and tier 3 when we had chemical reactions, and we had enthalpy changes. So we looked at delta H equaling NH. So that was kind of our first work in thermochemistry. We also used that for calorimetry, so we could make our system equal to our surroundings. Our delta H was equal to negative Q. And we just finished talking about Hess's law and heats of reaction. So when we talk about heats of reaction, you can see that we've got our little equation there that we've been practicing with. So having all of these in our toolbox, how can we decide which things to use and in what order to use them in order to come up with our final answer? So that is the example that we're going to take a look at, and it starts right down here. It says, what mass of octane is completely burned during the heating of 20 liters of aqueous ethylene glycol, which is automobile coolant, from negative 10 degrees Celsius up to 70 degrees Celsius. And they're giving us a couple pieces of information. The specific heat capacity for this aqueous ethylene glycol is 3.7 kilojoules per liters times degrees Celsius. They've also included a balanced chemical equation. So they're showing you, and I'm just going to use this as my cursor, they're showing you that if you take 2 moles of octane and 25 moles of oxygen, it will combust to create 16 moles of carbon dioxide gas and 18 moles of hydrogen or water in its gaseous form. And so using this information, how can we find the mass of octane? There's a few hints that come, or that I notice when I look at this question. And the first big one is that there's a temperature change. So right off the bat, when temperature change is involved, I know that Q is going to be involved. So that's the first thing I notice here, is that if I've got a temperature change, somehow I'm going to have to use Q. The other thing I take a quick look at is the fact that they're talking about two different things. They're talking about octane, but they're also talking about this ethylene glycol. And so as soon as you see two different substances in a question, I know it's been a while, but that should scream calorimetry. That should scream, okay, I've got a system and I've got surrounding here. If we're used to, and most 95% of the time, our surrounding is water. But in this particular case, instead of a calorimeter with water in it, we have a car engine and we've got some coolant in it, and the coolant is ethylene glycol. So ethylene glycol is going to be our liquid, it's going to be our surroundings. And what chemical are we putting into that ethylene glycol? We're putting in octane. So octane is our chemical, it's our system, and ethylene glycol is our surroundings. So right off the bat, I know that calorimetry is going to be one of those tools I'm going to have to use. It incorporates Q, so both of those things are going to be working together. Now, bottom line, how can I use this to find the mass of my octane? So what I would do is probably, I kind of start with what I know, and then if I have to veer off and find some other things later on, I will. So the first thing I notice, or the first thing that I start with is, okay, calorimetry. It's always a system, and it's always a surrounding. And so what we have here, just so we can remind ourselves, we've got octane, which is going to be our system, and we've got ethylene glycol, which is going to be our surroundings, just so we don't forget. So when we set up a calorimetry question, our delta H goes with the system, it's potential energy here, and our Q goes with the surrounding because it's a change in temperature, it's kinetic energy being changed here. We know that it's an exchange of energy, so we have to put a negative somewhere, so we park the negative with our Q. If we expand these questions, or these symbols or pieces of information, we know that we can find our delta H by taking the moles of our system and multiplying it by the molar enthalpy of combustion, because we're talking about combustion. And for our Q, we know it breaks up into MC delta T. In this case, we know the volume of our surroundings, so we're going to say VC delta T. V being the volume of our surroundings, C being the specific heat capacity of our surroundings, and delta T being the temperature change of our surroundings. I wanted to point out one thing here, this heat of combustion. Some people get pretty excited because they're like, oh, I know all of these H's. If I go to page 609, I can find the H for combustion, the H for octane. And you're right. If you go to page 609 and you look up octane, you're going to find out that it is, bear with me, I'm just looking for octane on page 609. Negative 250.1, negative 250.1 kilojoules. But be careful, that is not the H of combustion. That is the H of formation. It's H's of formation, but we're not forming octane here. We're combusting octane. So I want you to be careful there. Some people will quickly put in the heat of formation here for octane, and we're looking for the heat of combustion. They didn't tell us that. It's not on page 609. Don't panic. We'll be able to find it, but don't make that mistake. And this would be the moles of our octane. So I took a minute just to make a quick data table so we could kind of compare our system and our surroundings. And you'll see that we know nothing about our system. We don't have the heat of combustion yet for methane. We don't know the moles of methane. In fact, we're looking for the mass, so we don't know anything about our system. If we take a look at our surroundings, we do know everything about our surroundings. We know the, sorry about that. Let me do this. Let me bring that back up. Let me make it bigger. There we go. If we take a look at our surroundings, we know we have 20 liters of it. It's not a mass, but it's a volume, which is going to be okay because the unit of the C, see how it says kilojoules, and it doesn't say per kilogram times degrees Celsius, it says kilojoules per liter times degrees Celsius. So it's okay to use liters up here instead of mass. And we know we have a change in temperature, final T minus initial T, a change in temperature of 80. So we are great on the surrounding side, not so great on the initial side. And remember, we need to have at least everything but one in order to solve this right off the bat. So we don't have enough information to solve this right off the bat. The reason why is because we're missing this guy. So if there was only a way we could find that molar enthalpy of this equation up here. See, they didn't give it to us. This molar enthalpy of this equation. And I know, you're yelling at me right now. You're saying, oh, but we do, Miss Ryan. Yes, we can find the delta H of this guy really quite quickly. Now that we know that summation law, we can find the delta H up here, and then we can turn that delta H into an H. And you're absolutely right. So our first step is going to be, and I'm just going to send this over to the next slide. We're going to take this equation up here, and we're going to find the delta H. Okay? That's what we want to do. And it's the combustion of octane. So we are going to use our heats of formation. So we will use the heat of formation, but it's going to be used indirectly so that we can find the heat of combustion for octane. So I've done a little bit of work so that we can move through this a little faster, and you don't have to look at my horrible penmanship with my airliner. So I'm going to slowly bring this down and remind you that this is that summation law. This is how we're going to find the heats of summation, using page 609. Products first and then reactants. So here we go. Here's the chemistry. We're looking for the delta H of combustion. We need to know the moles and the H's for each of our products. We're going to add our products together, add our resultants or our reactants together. So forming those or coming up with that little equation and then plugging in some numbers. This is where page 609 comes into play. We can use 609 here because we want the heats of formation here. That's how you do the summation law. So we have 16 moles of carbon dioxide. That came from the equation, not to forget. It's way up here, but that's okay. The equation. Oh, good golly. Here's our equation right here. So there are 16 moles of carbon dioxide, 18 moles of water, 2 moles of oxygen, 2 moles of octane, and 25 moles of oxygen. So as we make our way through, and you guys probably have it solved already, we plug in these numbers, finding the heats of formation, and using our coefficients as our ends, and we come up with and tally and do the math, and boom, we find that we have 10,100. I'll just bring it up here so you can see the whole thing in the frame. Negative 10,148.2 kilojoules. Lots of energy. It's a combustion, of course there is. Lots of energy, right? We're releasing all of this energy when we combust. When we combust, how much octane? Right? This is our total enthalpy. And if you remember, it was for 2 moles of octane. So we have a total enthalpy here, but we want the molar enthalpy. You can't get molar enthalpy without total enthalpy. So we had to go and find the total enthalpy first, and then it's really quick because we know that if you take your total enthalpy, right, and you are looking for your molar enthalpy, you just have to divide by your moles. Good old formula we've used before. So we're looking for molar enthalpy. We take our total enthalpy, divide it by moles. Our total enthalpy that we found, the coefficient in front of octane, 2 moles, and we get our molar enthalpy. That's what we need for calorimetry. So yeah, we started out, we wanted to do calorimetry, but we realized that we were missing 2 pieces of information. We were able to use the law of summation to find 1 piece that was missing. So we can use this now. We now know the molar enthalpy, not of formation. That's on page 609. We did all this work to find the molar enthalpy of combustion. All right, we're there. Meaning we're 1 step closer to being there. So we have found our H. Going back, why did we find our H? Because we decided we wanted to do calorimetry, right? We set it all up, we were ready to go, but we didn't know this H. So we went ahead and found that H. So now, let's set that up again. Okay, so step 2, let's go back to our calorimetry. And now we have a missing piece we can put in there. So we have our change in temperature. We have our specific heat capacity. This was given to us in the question. We have our amount of surroundings, 20 liters. There's our negative sign. We did some work. Now we have the molar enthalpy of combustion here. We're just missing 1 thing. So we can solve for that quite easily. I underlined the kJ, the kilojoules, because you just have to make sure they're the same on both sides, right? This is measured in kilojoules, and the specific heat capacity, trying to get over there, is measured in kilojoules. So we're good to go. If they're not the same, we might have to do some converting, but in this case, they're the same. And so if you look at the units, the liters are going to factor out, the degrees Celsius will factor out, the kilojoules will factor out, and that leaves us with just moles, which is okay because that's what we want to solve for. So if we want to solve for moles here, we're just going to divide both sides by negative 5,074.1. And that gives us our moles of 1.2 moles of octane. So we were able to go back and use the calorimetry method only after we found the total enthalpy and molar enthalpy when we combust octane. One more step. It didn't ask for the moles of octane. The question asked for the mass of octane. So we're now going to take these moles of octane and convert them using our boxes to grams, and that's our third step. Take these moles of octane and boom, 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 boom. Using our boxes, we can find the grams of octane. And so our calculation works out to be 137 grams of octane. Okay, so 3 steps there, using lots of chemistry that we've used before. Then the knack to these multi-step questions is just taking a minute, looking at the question, maybe writing down what you know and what you're looking for, make a little table like that I did, and then decide what steps are going to be helpful and maybe what order I have to do it, right? So I wanted to use calorimetry right off the bat, but when I started to put my numbers in, I realized that I was missing 2 things, not just one. So then I said, well, is there any way I can find one of those things? And boom, the summation law was able to be used to find your total enthalpy of combustion for octane and the molar enthalpy of octane, the combustion of octane as well. And then it was pretty quick and slick at that point. I hope this was helpful. Remember, I'm around on Tuesdays and Thursdays at 2 o'clock for some extra help on the team site. And I will be probably posting the week 2 bulletin, which will give you your assignment and the resources you need to complete it. Okay, talk to you later. Bye-bye.